Okay, welcome everybody. This is Karen Grace Martin, and I am a statistical consultant and the founder of the Analysis Factor. And I want to welcome you to today's Craft of Statistical Analysis webinar, which is titled Structural Equation Modeling Using Partial Least Squares with SmartPLS. Just to give you a brief intro, partial least squares path modeling is a popular technique across many scientific disciplines, and at the same time, it's easy and powerful estimation technique for running structural equation modelings. It's great for robustness, prediction orientation, and can estimate even formative measurement models. And this is especially exciting for us today because we have our first guest presenter on one of these webinars. And our guest presenter today is Dr. Jeffrey Hubona. He is Associate Professor of Computer Information Systems at Georgia State University. And he has been using and teaching partial least squares structural equation modeling workshops for many years. So it's great to have you here, Jeff. We have a lot of people registered today, well over 100 people. So it's clearly a very popular topic. And I am looking forward to this presentation myself. I've used structural equation modeling before, but I don't know anything about partial least squares, so I'm interested as well. Okay. Before we get started, I want to do just a little housekeeping for anyone who's new using our webinar system. And I want to just do a brief introduction to why we're here, what we're about, and give just a couple announcements. So first of all, you may have noticed you're muted. We keep the line muted so that everybody can hear, to keep the line really clear. But at the end of the presentation, I'll open it up for questions. And when we get to that point, I'll explain how you can ask questions. In the meantime, if you have any technical questions, you can go ahead and type them into the question box. One thing I have found is if you find the audio is flickering, it's usually because your web connection is slowing down, especially if you're doing the audio over the microphone. So if you find, it's getting robotic sounding voices or something like that, you might want to use the telephone option for the audio. So just call in and you can get better quality that way. Okay, so let me just briefly tell you who we are and why we're here. So this is part of one of our Craft of Statistical Analysis webinars, and we do this every 6 to 8 weeks. We have one of these webinars, and it's one of the programs we offer at the Analysis Factor. We offer statistical consulting and a whole bunch of different training programs. This webinar series is one of them. And the focus of these webinars is really to help you hone the craft of implementing statistics by introducing different statistical methods that you may not have heard of, or maybe you've heard of them but don't know what they're about, or to clear up misunderstandings or confusion about different statistical approaches, because as I'm sure you know, there's lots of that going on. Let me just briefly give you a couple announcements. Our next webinar is going to be on July 28th. It's also a Wednesday. It's going to still be at 1 p.m. Eastern, and it's entitled The Other Regression Models, Part 1, Binary, Ordinal, and Multinomial Logistic Regression for Categorical Outcomes. And this is actually one of the very first ones I did, actually before we had the video system. So I just want to redo this one for you. it was pretty popular. So we're going to talk a lot about logistic regression and give you a good overview of that. We also, in just a few weeks, have a workshop coming up, calculating power and sample size. And we're doing that because that's one of those topics that get glossed over in statistics classes. So we're just going to review from the beginning how hypothesis tests, power, sample size, effect sizes, standard deviations, how they all work together. And even more importantly, I'm going to show you what are the 5 pieces of information you need to conduct a sample size calculation for any test and where to get them, because that's often the hardest part. And then I'm going to show you how to do that using 2 different sample size calculators. One is a free one that you can get online, and the other is a full sample size package. That is going to be June 24th from noon to 3 p.m. and registration opens on that tomorrow. So if you are interested, I suggest you go to that to the analysisinstitute.com, and if you click on calculating power and sample size, you'll find that registration page. We have a sign up there for getting on our advanced discount list. So you'll get a 20% discount if you sign up there today, so that you can register tomorrow. So there we are. Let's get started. Jeff, are you ready? Oh, now I don't hear Jeff. Can anyone else hear Jeff? Is it just me? Oh, no. Marsha says no. Okay, we tested this at the beginning. Hold on. Jeff, can you hear me? All right, hold on here 1 second. All right, let me see if I somehow muted Jeff accidentally. It doesn't look like it, but let's try unmuting him again. Try it now, Jeff. That's bizarre. It was working.
Variables that you cannot measure directly. They're typified by things such as attitudes and beliefs, constructs such as customer loyalty, things that go on inside our heads, so to speak, cognitively. And the purpose of structural equation modeling is to try and understand the reputed cause and effect relationships, the causative relationships between these latent variables. So you see arrows from so-called exogenous latent variables here on the left, or the independent variables on the left, and they have some influence on the dependent endogenous latent variables on the right. Okay, so these are things like attitudes and beliefs, and we can't measure them directly, so we measure them at a second level using typically surveys. Okay, we have things we can see. We have people respond to items in a questionnaire that assess their levels of these attitudes. And so we have these measurement items or indicators that are numeric data, and they comprise factors of the latent variables. For example, this one, PE, this latent variable PE, which actually stands for performance expectancy, is a composite of answers to these 4 questions about how well this software can help you perform a certain task. So we have these path models, and we're trying to estimate the path coefficients. Now, really, partial least square structural equation modeling is an extension of multiple regression. So if you're familiar with just plain regression and multiple regression, then partial least squares is just simply multiple regression, except you are solving multiple equations at the same time. So you can simultaneously determine the direct and the indirect effects among these simultaneous equations. Now, exogenous variables are typically the independent variables, as I mentioned, the ones that don't have any arrows pointing to them. And endogenous variables are the latent variables that are predicted, that are on the arrow side of these arrows in the latent model. Okay, and this model is the Utatte model. I'm in MIS, that's my field, and the Utatte model is the Unified Theory of Acceptance and Use of Technology. It's a user acceptance model. The nature of this, it's supposed to, these few constructs, these attitudinal constructs, are performance expectancy, effort expectancy, subjective norm, and facilitating conditions are supposed to predict behavioral intention to use a technology, which in turn predicts the future usage of this technology. So this is a typical structural equation model that is well published in my field. Now, if we step back, what we're actually doing here, I'm an academic, and I've published some papers where the analysis technique that I've used has been structural equation modeling. And typically what we're trying to do is we're trying to confirm or refute the nature, the strength of the relationships between these latent variables. And so what we'll often do is we'll attach hypotheses. We'll attach hypotheses to each of these paths in the inner model, and we will try and determine we will estimate the values, the magnitudes of these path coefficients, and we will perform some tests to see if they are significantly different from 0, if they're positive or negative, thus, affirming or not affirming our hypotheses. So we have the so-called plane of theory, which is the relationship among these latent variables, and we can't observe or measure or test the plane of theory directly. So what we do is we use the second level, these so-called measurement items that we can observe and measure, as a proxy, and we call that the so-called plane of observation. Now, structural equation models really have at least 2 major components. You have the so-called inner model, which is just the path relationships, and think of them as regression. Okay, in this case we are regressing eta sub 1 on psi sub 1, and we are regressing eta sub 2 on psi sub 2, but we're doing them simultaneously. Okay, that's one of the advantages of the SEM technique. It's a so-called second generational regression technique because you can estimate the path coefficients, the beta path coefficients, along several equations at the same time. And so we have the so-called inner model, which is the relationship among the latent variables, but we also have the so-called outer models, and the outer models are simply the measurement models. Here we have a measurement model which is comprised of these use 1, use 2, use 3, use 4 items that capture the nature of the construct for use. And we have the exogenous measurement model here on the left, these two latent variables that are captured by these measurement items. Okay, I know this is quick and dirty, and I shot myself in the foot by being off the air for about 20 minutes, but let me say a few things before I pull up the tool. Let me say a few things about the so-called advantages of PLS SEM techniques compared to the covariance-based SEM techniques. Advantages really is not the right term. In my field, in the literature, you will often see articles that try to assert that partial least squares is better than covariance-based SEM techniques for some reasons, and you see other articles that try to argue that the so-called covariance-based approaches are superior, are inherently better than PLS, and they'll cite their reasons for that. This whole argument, this whole normative argument, which one is better, really is misplaced. The fact of the matter is that PLS is more appropriate in certain circumstances, and the covariance-based approaches like Lizerl, EQS, and plus is more appropriate. And particularly, PLS does not have the distributional assumptions of MLE, of the multivariate linear estimation. That is, PLS is good to use when you don't know that your data set is normally distributed. Covariance-based techniques assume that you have multivariate normality in your data sets. Okay, so PLS has different data requirements, less stringent data requirements. Let's go through each of these one at a time. First, let me say a couple of words about no distribution. Again, PLS does not assume normality of your data, your observed data. Therefore, you can estimate the path coefficients without worrying about whether your data is normally distributed. It's very robust. Okay, it only works on numerical data. You have to have numerical data, but they can be nominal, ordinal, interval, or ratio, so you can have dummy variables. Your distributions can be non-normal. You can have, leftward leaning. They can be skewed to the left or right. It can be kurtotic, where it's peaked, where you have a high peakedness. You can have correlations. You can have correlations among your observed variables, and you still get pretty reliable estimates for the path coefficients and the other parameters in the model. PLS SEM techniques are better than covariance-based SEM techniques when you have complex models. Okay, and this is a model of medium complexity, believe it or not. With PLS techniques, you can estimate, you can have reliable estimates for the path coefficients, even when you have hundreds of latent variables and thousands of observed measurement items. When you have very, very complex models with the covariance-based techniques, the reliability of your estimates, the reliability and validity and the accuracy of your path estimates breaks down. Okay, so PLS, because of the way that it estimates the path coefficients, is pretty good with complex models, whereas covariance-based techniques are not so good. PLS also gives you pretty reliable path estimates when you have a smaller sample size. And some people, Win Chin, who's regarded as a leader in PLS SEM techniques, has published articles indicating that you could have as few as 10 times the number of predicted variables. Okay, so if you looked at this model, according to this benchmark, you would find the construct that has the largest number of arrows, which is this one, and according to the 10 times rule of thumb, you could get pretty reliable path estimates, path coefficient estimates, with as few as 40 observations, 4 times 10, according to this rule of thumb. But just like any other technique, the fewer observations you have, you're always better off with more data. Okay, but here's the point. If you have a very small data set, you're better off using PLS than covariance-based techniques. If you have a very large data set and or a very large complex model, you're also better off using PLS SEM techniques. But the flip side of this is if you have a model of moderate complexity and you know that your data set is normally distributed with no outliers, you don't have any missing data, and you have observations, you have from 200 to say 700 observations, you're probably better off using covariance-based techniques. PLS-based SEM, the way it works, it maximizes the R-squared of the predicted variables. The way the algorithm works, it's designed to maximize the R-squared for, in this case, for these two predicted endogenous latent variables. So it's often described as being a prediction-oriented technique, The PLS approach does not, unlike Lizral and EQS, there are no overall goodness of fit measures for the model like you have with Lizral. You can compare, using covariance-based techniques, you can directly compare the goodness of the fit of two models. You can't do this with PLS. Okay, so if you get a chance later, here's a handy-dandy chart that basically itemizes and summarizes some of the key differences between the PLS-based SEM techniques and the covariance-based SEM techniques. Let me, in what time we have left, let me call up the tool here and get the tool started. Hopefully you all can still hear me and you'll be able to see me when I start SmartPLS on my screen.
Hey, Jeff. I just want to say, I think it's fine if we go over a little bit. What I will do is if people have to leave right at 1 o'clock or 2 o'clock, I'll make sure I send everyone who's here the recording so that they won't miss the end. So don't worry about going over a little bit.
Okay. I'm seeing some things in chat. Jeff, is it possible to get your PPT slides? Yes, sure. Either Karen can give them to you or I will. Oh, there. Angela's already answered that. They're already posted. Okay. So there's the answer to that question. Okay, you should see a dialog box here. I started up SmartPLS, and the first thing it does, it asks you for a workspace. So I'm going to create a workspace. I'm going to say test June 9. Oh, SmartPLS is free. I should have mentioned this. Free for academics. The website, here I'll type it into chat, hopefully you can see this. The website is smartpls.de, smartpls.de, DE is Germany, and you have to register, but it's no cost to academics ever. So, and it's, I should tell you, it's a very popular tool. It's gone from no users to tens of thousands of users worldwide in the span of 4 or 5 years. And it's starting to hit it's already hit all the mainstream A journals in my field, but it's used by academics in economics, education, management, IS, finance, medicine. Just, it's really enjoys a wide user base, which is always a good thing. Okay, so I tell it the workspace, and the tool starts up, and I'll maximize it. Hopefully you can see this relatively centered on your screen. I'm going to close this welcome screen, and you can see SmartPLS. One of the nice things, it's kind of elegant in that it really has what I would call a minimalistic design. You don't have a really complicated user interface. It just simply shows you the menu choices and the drawing elements that you really need to operate depending on what you're doing. There are basically 3 windows on the left, and then there's a drawing space here on the right, typical of visual tools like this. You have a projects window. You have the so-called indicators window or measurement items window, and you have this outline window, which frankly is little used. So you're going to get most of your horsepower out of the projects window and the indicators window. Okay, so the first thing you would do, and these actions that I am tracing out on screen are actually represented in that second PDF slide deck in the zip folder in the handout that you can download there on Analysis Factors site. First thing you would do is you'd say File, New, and you would create a new project. You would name your project, and I'm going to call this, again, I'm going to call it Test June 9th. Test June 9th. And you want to make sure that this import indicator data is checked off. Okay, so let's put this in context. What are we doing here? We are drawing a path model, a structural equation model, that consists of latent variables, the round circles, and we can't measure the latent variables, so we're going to use our data items, typically survey items. Okay, path structural equation modeling is typically used in marketing, for example, to study consumer preference about a product or to study customer loyalty. Typical types of latent variables that you can measure by asking people to answer 3 or 4 or 5 Likert type questions where they respond on the basis of a scale, from an interval scale from 1 to 5 or 1 to 7, where 1 will represent strongly disagree and 7 will represent strongly agree. So you have these interval scales, so we have data. We're going to import our data to draw this structural model, and I've included a data set in your handouts, and it's a common delimited file. It's called TAM CSV, and we're going to open it up, and we're going to say next. And we tell it whether it has missing values. Now, if it does have missing values, you check this off, and there's some diagnostics that it will go through. Our data set that I have provided does not have any missing values, so I'll leave that alone. And we say finish. Okay, and you don't see anything happening. You say, what's going on? Well, you notice in the project window, we've created a folder, just like Bill Gates in the Windows folders, where we have the name of our project. If you click on the plus mark, then you will see a so-called SPLISM, which is SmartPLS modeling file, and you will see our original data file, the CSV file. The first thing you would do at this point is to double-click on the data file, and it will show you a preview. Okay, it shows you the first 9 records, and this is comma delimited. Like most SEM tools, you have to format your data file in a particular way. The first row consists of the names of the variables separated by commas, and then row 2 through, in this case, 1190 consists of numeric data. An important point to note about SmartPLS is that the data values must be numeric. They can be, nominal, ordinal, interval, or ratio, but you can't have text or character. You'll get errors if you do. Okay, so we look at that and it looks okay, and we say, okay, we want to start modeling with this data set. In order to do that, you double-click on the so-called SPLISM file in the project's window, and we'll do that. And you'll notice that all of the indicators now appear in our indicators window, and we have drawing tool. Okay, so we're going to proceed to draw a model. You'll notice that there are 3 icons in the toolbar, the taskbar up here, so-called selection, insertion, and connection. Selection, insertion, and connection. You will use these 3 tools quite a bit to draw your models. Okay, the first thing we need to do is to create our latent variables. We're going to drop some latent variables onto the screen, and then we are going to populate them with measurement items. Okay, so let me get a quick copy of this in front of me. Okay, so here we go. So I go into insertion mode. I drop a latent variable there, drop one there, drop one there, there. This model, by the way, is in your second slide deck. Okay, now I'm going to name these. This is going to be, I'm going to use the hot tools. This is going to be perceived usefulness. This one is going to be perceived ease of use. This one will be behavioral intention, or BI. This one will be attitude towards using, and I'll just call it ATT. And then we will finally have our predicted, or our penultimate predicted endogenous variable, what we're trying to actually predict with this model, which is usage of these computer applications. So I'll just call that use. Okay, you'll notice that the latent variables are red. Red is not your friend. The developers of SmartPLS, Christian Ringel and Associates, deliberately use color cues to tell you when things are bad, that is, you cannot estimate the parameter values, red circles, for example, and when things are good. When things are good, the circles turn blue. That means you have an estimable model, a model that can be solved with the PLS algorithm. Okay, so we have these latent variables. Now we need to associate measurement items. Okay, attitude is measured with, okay, and I'm just going to shift. I'm using Windows 7 Mac. The commands are a little different, but it works just like it does with any Windows application. You can shift and select a whole range, and I'm going to grab this at 1, 2, 3, 4, 5 are the data items. Those are the 1 to 7 responses for people who filled out the survey about their attitude towards using this computer, whatever computer application. Okay, so attitude now is associated with these 5 measurement items. Let's call out the behavioral intention. We'll associate BI1, BI2, BI3 with the latent variable behavioral intention. We will grab the data items EOU1 to EOU5, and let's see here, we've got a problem. Let's put this down here. Go back up here. We're going to rename this. This should actually be perceived usefulness. this one here should actually be perceived ease of use. I was talking and I wasn't watching what I was doing. Okay. Okay, these are the for use construct, the for use measurement items. They go over here. And then finally, we have 5 measurement items for perceived usefulness. Okay. And I'm going to pretty this up a little bit. I'm going to align them top, get the measurement items out of the way so I can draw paths. Let's see, and we'll align them bottom, and we'll, I'll tell you what, let's do this. Let's align them to the left. And let's align BI to the top. Oops. And use, we will align right. Okay, so now we've created in our drawing tool the latent variables, the constructs, perceived usefulness, perceived ease of use, behavioral intention, attitude, and use. And we've associated them with measurement items, responses to the surveys. Now we're going to draw the path linkages to complete the model. Note that the latent variables are still red, meaning that if you tried to estimate this model, it wouldn't. The software could not estimate it. We have to link the latent variables with each other. So we go into the connection mode, and we start drawing paths. We'll draw a path from perceived ease of use to usefulness. We'll draw a path from perceived usefulness to behavioral intention. We'll draw one from perceived usefulness to attitude. From attitude to BI. And then finally, from BI to use. And notice now, at this point, whoops, I didn't want to do that. Notice our model turns blue. And the blue model means that if we tried to run the algorithm and to estimate values for these path coefficients, we would get a result. Okay, we need one more path in here. Okay, so we're done. Okay, so now we've drawn our model, and what we're trying to do is we're trying to estimate the path coefficients, just like regression coefficients. All of the data is standardized when you import it. So you can interpret the path coefficients as showing the magnitude of effect. You know, how much influence does perceived usefulness have on behavioral intention? Well, that influence is reflected in the magnitude and the significance of the beta path coefficient, which is just the same thing as a regression coefficient. It can be interpreted in the same way. Okay, so let's run the PLS algorithm, okay, and we have to make sure that our model is highlighted to do that. So we're going to calculate. We use the calculate menu, and we say run the PLS algorithm. And these are all default settings. We can just leave them alone. Say finish. Okay, and now you see the model is suddenly populated. Let me briefly explain what these numbers all represent. Okay, the numbers, this is the so-called outer model that I showed you previously, or measurement model. Okay, this is the outer model or measurement model. And these loadings, these numbers, and you'll notice they're all ratios between 0 and 1. These are the factor loadings for each of these measurement items on its respective latent construct. For example, this is behavioral intention, this latent construct, and behavioral intention, this whatever it is, this latent construct, explains 85% of the variance in people's responses to BI1, the survey item BI1. And the latent construct behavioral intention explains 83% of the variance in BI2 and so forth. Okay, so these are just the same things as loadings and factor analysis. Okay, so if you do a factor analysis and you get the loadings, that's what this is. Okay, and this is the so-called outer model or measurement model. You want these loadings to be approximately 0.7, 0.8, 0.9 in that range. You want them to demonstrate to be valid, to be reliable, valid predictors, and they need to be of the magnitude of about 0.7, 0.8 at least. Okay, now in the inner model, we see these arrows or paths pointing from one latent variable to another. This path coefficient is 0.40. Okay, all of this data, when we input this data, it's all standardized by the software, which means it has a mean of 0 and a standard error and a standard deviation of 1. That means that when the levels of perceived usefulness increase by 1 standard deviation, then that will have a 0.4 impact, 0.4 standard deviation impact on levels of behavioral intention. So, or put a simpler way, when perceived usefulness goes up by 1, that drives up behavioral intention by 0.4. Okay, so all of these, we can see that all of these path coefficients are positive, but are they statistically significant? That is, do we know for sure that they're all significantly different from 0? They're positive, but how do we tell if they are statistically significant? We'll get to that in a second. The numbers inside the predicted endogenous variables, such as 0.198 here for perceived usefulness, these are the R-squared numbers. Okay, in this figure, 0.198 means that 19.8% of the variance of perceived usefulness is explained by the factors that predict it, which in this case is only this one. Perceived ease of use is the only latent factor that has an arrow pointing to perceived usefulness. So as perceived ease of use goes up and down, it explains almost 20% of the variance of perceived usefulness going up and down. Okay, and here behavioral intention, the R-squared is 24.3%. That means that roughly 24% of the variance in behavioral intention is explained by the 2 factors that point to it, that have causative paths directly at it. Now, a couple of things I should say about this. One of the advantages or one of the good things about structural equation modeling and about so-called second generational techniques, which structural equation modeling is an example of, is that you can simultaneously estimate the direct effects, for example, the effect of perceived usefulness on behavioral intention. We know that there is a path connecting perceived usefulness to behavioral intention. This is a direct effect. As perceived usefulness goes up and down, behavioral intention goes up and down by 0.4. But we can also, at the same time, we can estimate, we can capture the indirect effects. For example, in this model, perceived ease of use has a direct effect on perceived usefulness, and perceived ease of use has a direct effect on attitude, but perceived ease of use also has an indirect effect on behavioral intention through usefulness and through attitude. That is, because we have paths going from perceived ease of use to attitude and a path going from attitude to behavioral intention, perceived ease of use is indirectly driving behavioral intention up and down as mediated through attitude and as mediated through perceived usefulness. In regression, you would be estimating each one of these paths by itself in isolation. Okay, if it's multiple regression, you would have, let's say we're trying to estimate this with multiple regression. We would have one equation. BI would be the dependent variable, the y variable, and we would say BI is a function of or is regressed on two other variables, on perceived usefulness and attitude. So if we were trying to solve for these path coefficients using regression, we would have to separately do one multiple regression for the impact of attitude and perceived usefulness on behavioral intention. Then we would have to do a completely separate regression, a single regression, for the impact of perceived ease of use on perceived usefulness, another single regression for the impact of perceived ease of use on attitude, and then yet another multiple regression where we regress use at the same on BI and on attitude. So we would be solving this, if we were using regression, we would be solving this with 1, 2, 3, 4 separate independent regression, single regression and multiple regression equations. The one big advantage of structural equation modeling is you can estimate all of these direct and indirect effects together. And it captures the way that it computes the path coefficients, which is beyond the scope of this webinar. It simultaneously captures the direct effects and the indirect effects. Okay, so that's important to note. Now, I mentioned previously, how do we know if these path coefficients are significantly different from 0? That is, what are the confidence intervals? You know, normally if you're using multivariate normal techniques, you could figure out what the confidence intervals were for each of your beta path coefficients. Well, if you recall in your statistics, those techniques typically assume that you have multivariate normality, that your data is normal. And in fact, the technique to estimate the confidence interval assumes that you have normal data. You have normally distributed data, your observations. Okay, PLS path modeling does not make that assumption. Therefore, you cannot compute confidence intervals. You have to use so-called bootstrapping techniques. And bootstrapping techniques are the non-normal analog to computing confidence intervals. What bootstrapping techniques do, and we'll talk about it just briefly. We could talk about that one topic for an hour or two if we wanted to, but it takes your original data set. Let's say we have 1,000 items. You know, we've had 1,000 people fill out surveys. So in our data file, we have 1,000 records with observations, with responses to people's survey questions. What bootstrapping does is it will resample from your original 1,000 observations over and over and over again and estimate the model. It will take a different mix of your observations. It will estimate the model, figure out what this path coefficient is, then put all of the observations back and start over. Then it will take another resample from your observations, your data set. It will estimate the model. It will record all of these path coefficients. It will put the data back. Then it will do it again and again. Each time it is resampling, it's drawing a different mix of your items, and so each time it resamples and estimates the model, it's getting a different value of your path coefficients. So it keeps calculating the path coefficients, and they vary. Okay, they 0.2, 0.3, 0.4, 0.5, 0.6. You get this variance. That is, you're getting a measure of the standard error by resampling, and you know what the mean is. The mean is 0.4. So you can figure out the t-value, which is just the mean of the parameter divided by the standard error. Okay, if you know the t-value, you can look it up in a t-table. If you know the t-value and the degrees of freedom, you can look it up and you get a p-value. P is less than 0.05. Okay, generally, when you get a path coefficient, when you have a sufficient sample and a decent sample, a representative sample, and you get a path coefficient that's 0.2 or greater, it's generally statistically significant. But you really need to do the bootstrapping, and you do the bootstrapping here in the software. Calculate bootstrapping, okay, and you tell it how many original observations you have, which is 1190. We're going to resample, let's say 200 times, and we say go. And what it's doing here, from my 1190 original observations, it is drawing 200 separate samples of 1190 items, a different mix of 1190 items, 200 times, and it's estimating the path coefficients over and over and over again, which is why it takes a while. And the output, these are t-values, not the coefficients, not the p-value. If you remember from your statistics, if you're conducting a two-tailed test, you want a t-value that's at least 2, plus 2 or minus 2. Okay, a t-value of 1.96 actually, if you have 100 degrees of freedom or more, is significant at the 0.05 level. So we can see these t-values are all greater than 2, so we know the path coefficients in the inner model are significant. Now if you look at the outer model, these are also t-values. Notice how high they are. You know, recall that a t-value of 2 is statistically significant. These t-values are 30, 40, 100, extremely high. You know, is that weird? Is that wrong? No. The measurement model is held to a different level, a different standard, a different level of quality. Your measurement model, you know, we're doing a two-step process. We are trying to build in your specification of your model, you say, okay, well, these particular survey items are associated with this construct. These survey items are associated with this construct. These survey items associated with this construct. So in the specification of our model, we first create a measurement model, which has to be good in order to be able to look at the coefficients in the so-called structural inner model and give them any credibility. Okay, so we have two models, the measurement model and the inner model, the structural model. Now, if our measurement model is no good, the outer model is no good, then we can't even look at the values for the inner model. Okay, thus, there's a different level of standard for the t-value. You want t-values in your outer model to be extremely high, whereas in the inner model, you know, if they're just 2 or better, you're okay, you're good to go. Okay, so let's run the PLS algorithm again. This is it. Okay, SmartPLS. Let me show you a couple other things about SmartPLS. You get reports. Okay, so this is the PLS algorithm. These are if we have associated hypotheses, we're testing a theoretical model, and let's say we are revising the model, we're adding a latent construct or two, and we want to test the significance of the latent construct. We would say, okay, I'm hypothesizing that perceived usefulness has a positive effect on behavioral intention. And we test that hypothesis by getting an estimate for the parameter, 0.4, and looking at the significance. And we would look in this example and we say, yes, if my hypothesis is that perceived usefulness has a positive impact on behavioral intention, this parameter estimate validates or affirms that hypothesis. Similarly, we could have hypotheses attached to these other paths, and this is what we would report in our research paper. Okay, SmartPLS puts out reports, so-called default report, which gives you a whole range of statistics. The output report, one of the beauties of the design of SmartPLS is it basically outputs everything that the model computes in chronological sequence. That is, when you look at your default report from SmartPLS, from running the PLS algorithm, the stuff at the beginning, the top of the report, is the pre-processing stuff, and the stuff at the end is what you are interested in, the so-called quality criteria. And so as a user, as a consumer of SmartPLS, you're trying to validate, you're trying to write a paper and publish a paper that validates this model. You would create the model, you would estimate the model, and the first thing you would do is you'd open up the default report and you'd go down here at the bottom and you'd look at the total effects, and these are just simply the path coefficients, and you would look at the so-called average variance extracted for each latent construct. AVE is a measure of convergent validity. That is, these latent constructs should be unidimensional. Okay? Perceived usefulness is something you can't observe. It's something that is measured by these measurement items, but it should only have one dimension. Okay? Behavioral intention, similarly, is a different latent construct, which is measured by BI 1, 2, and 3, but this should also be one dimension. And these two dimensions, whatever perceived usefulness measures and whatever behavioral intention measures, these two dimensions should be separate from each other. They shouldn't overlap. Or stated a different way, they shouldn't share a lot of variance. Okay, they might share some variance, maybe as much as 50%, but if they share more than 50%, you've got a problem. Okay, so they should be distinct unidimensional constructs. Now, AVE is one measure of that unidimensionality. Because the data is standardized, AVE is between 0 and 1, it's a ratio, and you want it to be as close to 1 as possible. You certainly want it to be up above 0.6, 0.7, and you see that all of these are except for use. Okay, composite reliability is another measure of the measurement reliability for each individual construct. It's very similar to AVE. R squared is the amount of variance that is explained in each of these predicted latent constructs. And you want R squared to be high, right? That's the point of these models. These models are supposed to be predicting what goes on here at the end. Notice perceived usefulness, 12%. This whole model, very mature, very well-published model, in this data set only explains 12% of the variance in usage. That's not much. What that says, the flip side of that is that this model doesn't explain 88% of the variance in usage. Okay, and you might say, well, Jeff, that's not very good. Your model is not very good. You know what? Actually, this is a very mature model. This data has been published. I published it with some other people in a number of articles. This is noteworthy because the R-squared is kind of low. This is a very mature, well-tested model. There are thousands of papers in my field about technology acceptance. The fact that it's only explaining 12% in this case is kind of noteworthy. What else do we have here? We have Cronbach's alpha, which is a measure of the reliability of your measurement items. Okay, anyway, the point, without trying to explain, as a user, when you're writing a research paper, okay, cross-loadings. Okay, this is the same as a factor analysis, where along the top we have the latent variables, and along the side we have the measurement items. Okay, and what you want for any set of measurement items like attitude 1 through 5, right? You want these factors, these factor loadings, to be high for attitude, but you want the factor loadings for these attitude items to be low on the other unrelated constructs. Okay, that we want it to have high convergent validity. We want these measurement items to converge highly on its own respective construct, but we also want it to have discriminant validity. We want these factor loadings to load lowly, if that's a word, on the unrelated constructs. Okay, that's what we get out of this. These are the factor loadings and cross loadings, and this is an orthogonal rotation, by the way, which is typical in PLS. PLS is called component-based SIM. Orthogonal rotations tend to overestimate their loading. So for attitude 1, 2, 3, 4, 5, you'll notice that it's loading quite highly on the attitude construct, and the cross loadings are lower. Okay, the cross loadings, the loadings of the attitude measurement items on BI are only in the 0.3s. That's what you want. And same with the loadings, the cross loadings of attitude 1, 2, 3, 4, 5 on perceived usefulness in the 3. That's what you want. You want the same with BI. Okay, BI loads highly on its own construct, and it loads lowly, if that's a word, on its unrelated constructs. Okay, I've sat here and run off and yammered on. This might be, Karen, do you think this might be a good place to stop and maybe take some questions?
Sure.
Okay.
We actually have quite a few questions, and
okay.
It's 2:21. I know you said you had to leave at 2:30.
I can fudge by a few minutes.
Okay. What I'm going to do, first of all, everyone will get the recording, and we had one person who had their hand up, so let's start there, and then I will read through the written questions. Mark Schneider, I'm unmuting you. Hi, Mark.
Hi.
Do you have a question?
I do not have a question.
Oh.
No.
Okay.
Maybe I pushed a button by mistake. I'm sorry.
Okay, no problem. Okay, Mark's muted again. All right, I'll start reading off questions then, because I think he was the only person. Anthony asked, can SmartPLS be used to do a CFA? That's confirmatory factor analysis. A few people asked that. Uh-oh, Jeff, did we lose you again? Can you guys hear me? Okay. Huh, I wonder if it's when, oh my goodness. Okay. No, he didn't leave, because we can still see his screen. You know what we will do is the system saves all these questions. So rather than mess around with the trying to get this audio back again. I'll just make sure he's not muted somehow. No, he's not muted. Okay, what I will do is I will send him all the questions that people have typed in. So if you have a question, go ahead and type it in right now. And I will give Jeff these questions, and hopefully he can ask them back or answer them, and we will get you those. Let me just send him a quick chat. I don't think he can see the questions. He can see the chat, but not the questions. Okay, he says right. So he is still here. I'm just trying to think if there's a way I can get him the questions. Okay. Without. When you guys send the questions, do you have an option to send to all? If not, Jeff, we might have to follow up with the questions and do written replies, and we'll send it to everybody. I don't know if that's, I don't want to promise that you'll do all these. But actually, this will work. I'll read them off if you want to type some answers in the chat for just a few minutes. So the first question was, can you do confirmatory factor analysis? If you can type that into the chat and send it to all, everyone will be able to see it. He says, okay. So everyone keep an eye on the chat. All right, and I'll just keep reading off questions. So he says not, you can all see that, right? Sorry, question panel's very small. In PLS, is it customary to build your model in stages, starting with the basic model and then adding in moderating latent constructs, essentially building from the ground up in line with your theory? Elizabeth says she can't see responses. You have to look in the chat, not the questions. You should see his answer to the first one in chat. Can everyone see the chat? Where is the chat? No. Huh. Oh, you know what, Jeff? When you have to make sure it says all entire audience when you send your chat. It looks like those just went to me. Okay, so anyway, his answer was, can't do a CFA like you normally do, has to be in a structural model. And then the last answer was, yes, with moderation in particular. Yes, they can see you. We can still see your screen. There you go. He's opening word, answering them right in there. Perfect. Can everyone see that? Oh, Elizabeth says, great idea. Yeah, that looks great. Okay. Not like Lizzo. Okay. Okay. Oh, another. Can you do SEM using PLS with Amos? Okay. Like in SEM, can we use sum of items instead of items in the measurement model? I have one variable that has one item. Can I still use this? All the other variables have several items. Okay. Can you give us a few good references that address the pros and cons of PLS versus covariance-based SEM? Okay. I'll make sure everyone gets those. In the end, how do you know when you've developed the best possible model using SmartPLS? How about multicollinearity? How does PLS work with that? Can indicators be measured on a nominal scale? Yes, no. Can I import data from SPSS or another stats program, or do I have to first convert my data to a CSV file? Can models based on covariance and PLS be compared, and by which criteria? Okay. Jeff, can I please confirm that the minimum number of cases for this model would be 50? No, fewer. Did you mention a rule of thumb for the measurement model coefficients? Jeremy, do you mean the factor loadings? Yes, factor loadings. You mentioned something about missing data earlier. How does PLS deal with missing data? Ooh, let me just, not mean replacement. Okay, sorry. We just finished missing data workshop and we talked about all the evils of mean replacement. So that's my little thing I'm throwing in there. Okay. Is PLS suitable for latent growth modeling? do we have to standardize the data before using PLS? How will this model account for errors in the indicator variables? I assume this is Leon. I don't know if you're still here, Leon. Oh, long answer. I assume he didn't mean measurement error. I know in AMIS, every endogenous variable has to have an error term, but maybe those are observed endogenous variables, now that I'm thinking about it. All right, hold on. Let me see if Leon says yes. Yes, measurement error? Or do you mean just residual error? He says yes. Okay, interaction. I'm trying to get to the interaction question. Sorry, there's so many questions. I'm trying to find the interact. Can you do moderation? I think that's what it was. Interactions. There it is. Is testing for moderation interaction effects possible in PLS? You already shown mediation. What about moderation? Oh, great. Oh, Jeff needs to go. Okay, I will check to see if there are questions that were not answered. Thank you all very much. Jeff does full workshops on this, web-based workshops. So go ahead and check out his website. So if you want to learn more about that, oh, there's one next weekend, June 18th. So if you want to learn more, that would be a great way to do that. So thank you, everyone, and thank you for your patience putting up with our technical glitches, and I'll make sure everybody gets the recording. Thanks, bye. And thank you, Jeff.